especially Fuse on EAP and Valfly Camel. Earlier, I did the same for JBoss EAP and Valfly. In my free time, I like hacking in developer, in build tools, such as source dependencies for Maven and Gradle, or editor config implementation for Maven and Gradle. Today we are going to speak about Quarkus, and we will start with a very short demo. Then I'll try to explain what is Quarkus, how it works internally, and if there's time, I will show you more demos. So let me show you how short a demo can be. So first, let's have a look what's there. I have built it already because I don't want to bore you with Maven output and so on. But what's there in the target directory? There's an executable. I hope you can read it. No, you can't. This is better. So there's an executable. It's a native executable that you can run on console without using Java, without using Java runtime environment. It is 19 megs big or small. Is this nice? Yes. And let's start it. It has started instantly in 4 milliseconds. Is this nice? Yes, it is. Let's check how much memory it is spending. There's like 13.5 megs. Is this nice? Yes. It's a Java web application with a REST endpoint. Have you ever seen something like this? I don't think so. Does it work? Yes, it works. Good. I hope I kept I have awakened your interest, and let me important notice. I have posted the slides on Twitter, and my Twitter account is here at the bottom, and you can download and have a look at the slides later if you want to. So the short demo is over, and let's have a look what is Quarkus. First, the name. It consists of quark, the elementary particle, and us, the hardest problem in the software. When we want to classify it somehow, it's a toolkit in the first place, and a framework too. I say it's a toolkit in the first place because and it's not only for Java, it's also for Kotlin. When I say it's a toolkit in the first place, it's because if you are going to do, you as Java developers, if you are going to do the normal, usual, common things, Quarkus is going to be only a part of your build setup, either as a Maven or a Gradle plugin, right? And as a very general, this is the typical workflow. The input for the Quarkus tooling are compiled Java classes. Quarkus takes them and generates an optimized jar out of them, which can be run either on a stock JVM, such as OpenJDK, or it can be passed to GraalVM. Who of you has ever heard of GraalVM? There are some. We will come to it later and explain more. And it can be passed to GraalVM, and GraalVM can produce a native executable that I have shown you at the beginning. Okay? So when I say this is primarily a tooling for you, how are you supposed to write your applications? You are supposed to use well-known and well-established standards that exist today. On one hand, we have these old Java EE standards like servlets, JAX-RS, persistence, bean validations, and so on. And on the other hand, there are these newer MicroProfile standards for cloud-native things like health and Open API for tracing, Open Tracing for tracing, and so on. These standards have well-known implementations such as RESTEasy and Hibernate that you will find in Quarkus. But it's not only standards, it's also something more. There's things like Jetty, Apache Camel, Apache Kafka supported inside Quarkus. And they should work for the most common cases out of the box. And there's also Vertex. And it means that you can use both imperative and reactive styles of programming on the same platform. Quarkus was designed with developer in mind. And it means that it is easy to start with due to known technologies, as I have shown already. But there's also more small little things that make your developer life pleasant and easy, such as live reload in the development mode. You can code your endpoints, change things, and when you hit the endpoint, it's reloaded for you automatically without you to need to rebuild and redeploy and so on. That's Maven and Gradle tooling, and there's support for Java and Kotlin. Further, Quarkus was designed with containers in mind. They are primary and very central to this technology. What does it mean? It means that the artifacts that Quarkus produces are small. The basic case with native executable is just 19 megs, which I shown you at the beginning, right? Why is it important? Because when we produce Linux containers, we don't want them to be too big. We want them to push to remote container registries fast. We want deployments inside Kubernetes clusters to go fast. And this has to do with the size of the container. We want fast boot time, which Quarkus does a lot for, right? And why is fast boot time important? Because we want fast scale up in environments like Kubernetes. And not only there, there's serverless and there's cold start. And when you are cold starting a container in serverless, it's very nice to have a Java application up in tens of milliseconds. And third, Quarkus was designed for low memory footprint. What's important? Memory is what you pay for on Amazon AWS and whatever else public container provider, public cloud provider, or even if in your own data center. So with the same amount of RAM, you can start more containers. And it can save you a lot of money. Okay, let me show you some numbers. First, how do we measure memory consumption? In the world of Java, there's a lot of concepts like heap size and so on, which are interesting and important in their own right, but in the container environment, what matters is the overall amount of memory the given process is spending. And for example, PS minus O RSS is a way how to find the number. Okay? So let's compare the native executable I have shown you at the beginning with the optimized jar run on a conventional JVM, in this case OpenJDK, with a traditional cloud native stack that you probably use today. So if the numbers for the native executable are like between 10 or 20 megs, it's roughly 10 times more with a traditional stack. And probably all of you know these numbers, and they are not different, not very different if you use Wildfly or even things like Jetty or Tomcat, right? There's not much that you can save there. And that's what Quarkus is doing with some radical solution for this. These numbers are for the simplest REST application. If you add persistence with a connection to a database, it increases roughly like this. Okay? The boot time. The self-reported boot time given out on a console by an application server is interesting, but not necessarily useful when you are measuring this for the sake of comparison in the cloud, because application servers typically use lazy initialization. And when they self-report that they are started, it doesn't necessarily mean that they are ready to serve requests. And to make the numbers comparable, we say what matters is the time to the first request. Just for your curiousness, this is how it's possible to measure something like this. You construct a simple endpoint that outputs a timestamp on the console, right? Then you start the request generator 100 times per millisecond. You start off your application, but before that, you output the current timestamp on the console, and that's the first one, right? And when this curl succeeds, that should be the last timestamp you get, and then you can simply subtract the first one from the last time, and you get the number in milliseconds. That's the useful piece of information. So when comparing, I hope you can read it, but when comparing, again, the native executable with the optimized jar and with the traditional cloud native stack, the boot time, or the time to first request is roughly like this. It's tens of milliseconds in the simplest REST case for the native executable. It's under a second for the optimized jar on a conventional JVM. And with a traditional cloud native stack, it's like 4, 5, 6, 7 seconds. Okay? You surely know what's the number for your application using whichever Spring Boot, Tomcat, Wildfly, right? So how are these numbers possible? So let's have a look. What is Quarkus doing for you? As I've said, the traditional application server is doing a lot of things during the boot. There's lots of code implemented in a lot of classes that are used just once, and they spend time when they are executed during the boot and during the deployment of your application. There's annotation processors, XML parsers, and in an application server like Vaultfly, this is really hundreds of classes that span the memory during the whole lifetime of the application server, even though they are not used anymore. What can be done? And this is the central trick offered by Quarkus. It's called Build Time Boot. We just spin up a special JVM at the build time, and we try to do as much as possible inside this build time JVM, and we simply record what happens or what should happen at the real runtime. And the recording is just some bytecode. That's the magic that happens inside Quarkus. And that wiring, it's hard-coded startup of your services. Like if you use CDI, CDI is totally dynamic during deployment and boot. Injection points need to be identified, injection objects need to be found, and all of that with Quarkus is done at build time. And the result is the hardwired code that wires all the points, all the injection points with the objects that should be injected. And there's two options where this wiring boot code can be placed. First, it's either a static initializer in some class, or it's a main method. What's the difference? Because there's an option for you to use GraalVM later, and because GraalVM is able to perform further optimizations with static initializers, those initializers or putting this wiring code into the initializers is preferred. When it's not preferred or not possible, it's only when there's some access to files or sockets or other runtime resources necessary, right? So if you need to open socket, read a file at runtime, you need to place that code to main, not to a static initializers. So maybe just what's the time? Okay. For your curiousness, what would it look like? In the target folder, Quarkus will produce the wiring classes here, and there will be here the main. You probably can't read it anyway. So the main is just invoking the. What's happening? Okay, let's close this. Okay, let's stay with the presentation. So the wiring is recorded, and it's just a bytecode that is run for you at the runtime. So when you look at Quarkus internally, it basically looks like an application server, but it's not an application server. It's built on just a build-oriented container that runs for you at the build time. Yeah? There's some components there that exist for a long time in Wildflight, like Gendex for class path scanning, and Gizmo. Gizmo is new for bytecode production. That's the recorder for the bytecodes. Graal SDK is used directly for the production of the native executables. Then there's some Maven and Gradle plugins, and lots of extensions. Those extensions are there for you to do the magic. And they basically look like those pieces of code that are run during the deployment of your application inside a regular application server. So they are there to resolve to process annotations, to read XML configuration, and to produce the wiring as a bytecode. So if you are interested in this idea, you can join the community. The concept of extension is designed to be general enough for people from community to provide new extensions. And as far as I know, there's a registry for extension planned where you can put your extensions so that other people can use it too. So the contributions in this area are highly welcome. What's the time? Okay, let's go to GraalVM. So GraalVM is there to produce native executables out of optimized jars. When we hear of Graal, there's two distinct things that are called like that. First, it's the Graal compiler that can be used as either as a JIT compiler inside a regular JVM, or it can be used as a ahead of time compiler together with inside GraalVM. Right? That's the first Graal name, and the second one is GraalVM, which is the polyglot VM. There's a lot of things there in the GraalVM, under the GraalVM umbrella, and Quarkus is using just some of them. And it's the Graal compiler and the SubstrateVM. So for the rest of this presentation, GraalVM is going to mean just the Graal compiler and SubstrateVM. So what does it mean to compile ahead of time with GraalVM? It means to combine classes from your application with the classes from the JDK API and with the classes of the SubstrateVM. SubstrateVM is something you don't need to know much about. It's just, how to call it, some augmented special code for native executables that is either replaced inside JDK API or that is there as an addition. And the result is a statically linked executable. What happens during this process? There's a lot of static code analysis under the closed world assumption. Closed world assumption means that everything that will be needed on runtime is known at build time. This allows lots of optimizations, but on the other hand, this is imposing lots of limitations that you need to know about when working with native executables or when writing your things. And actually, Quarkus is aiming at isolating you as a developer from all these things, but they are still good to know. So under the closed world assumption, we can eliminate lots of code that is not needed at runtime. We can throw away whole classes, we can throw away fields, methods, or execution branches that we know won't be executed at runtime. And this is what GraalVM is doing for you. On the console, when you work with the stock GraalVM, this is the command you would use to produce a native executable. It's called native image. jar is an input, and the output is the native executable, right? And these are all those advantages we get out of it. Fast start, less memory, and small disk on site, on small disk size. So what limitations is this imposing? There's no dynamic class loading. And you probably know what this means. This means that no traditional application server can ever work on top of GraalVM, because deploying wars and jars is nothing else than loading classes dynamically. Yeah? That's why Quarkus is doing all these things at the build time. Second, no native interfaces. What does this mean? No agents. Like JRebel, Byteman, profilers, and tracers possible when you run a native executable. Why? Because most of these interfaces rely on bytecode. And when you produce a native executable, there's no bytecode there. Second, there's no Java debugger. Sad, but true. But there's still, it's a native executable, and the GNU project debugger still works. It's not easy to work with, but still possible if you really need it. But not to need to step through the native instructions. If you want to step through Java source code, you need GraalVM Enterprise. That is a paid version of GraalVM. But for your convenience, it's still there. Okay? There's much more there that is unsupported, that you perhaps don't need, but you need to know it, like security managers, finalizers, invokedynamic. That's interesting. This is not a big issue for Java and Kotlin. If Java and Kotlin are using this, it's only for lambdas. And those things are transformed to methods by GraalVM to overcome not the unsupportedness of invokedynamic. But if you want to support for a language like Ruby that uses invokedynamic very often, it's a problem. Good. Reflection is very limited. Why? Because it's against the closed world assumption, right? And it just needs registration upfront at build time. So you need to mark, if you work with the plain GraalVM, you would supply a huge JSON file with all fields and methods marked for reflection, and it would work, right? And this is also something GraalVM helps a lot. For things that GraalVM wouldn't find itself, there's a special Quarkus annotation register for reflection for you. And very similarly for other things like dynamic proxies, resources, JNI, unsafe, they all need to be registered at the build time for GraalVM. Static initialization, that's the thing I have already mentioned when speaking about what is Quarkus doing. GraalVM is optimizing heavily everything you have in your static initializers. So it resolves all the classes and runs all static initializers at build time. It takes a snapshot of the produced heap and it just puts it into the native executable. And this is why the boot time looks like what you have seen. It's just a stored heap that's loaded into the memory and it's there. There's no class resolution. There's no static initializers run. It's just image of the memory. It's there and it started. Okay? But there are some downsides, as I already mentioned when speaking of Quarkus. You may not use file handlers, sockets, and threads there. So, to sum up, GraalVM, when working with it directly, is very hard to work with. You have to produce big configuration files to register reflection and proxies and all those things. And it's exactly where Quarkus comes in and works the stuff for you so that you don't need to take care. So, what's the time? Yeah, we have some time. So let me show you more demos. With every slide in this part, there's a URL at the bottom that you can visit, and that gives you the guide that I'm basically showing in this demo. And the documentation is very nice there. Please go there and try. It's mostly very, very, very easy. So there's a Maven plugin that aims at producing stub projects. I have run it here already. So if I'd run it once again, it would probably fail, but you can specify things like group and artifact ID and the class name for the REST entry point and the path it should produce. If you look at the ID will fail, which is very funny. So there will be no IDE. It may not be maximized. Okay, let's try it. No. So this is the project. Can you read the POM? Probably not. Let me increase the font. I hope you can read it now. So we would import a Quarkus BOM. You would have some dependencies that are initially set up by the plugin, and you would have a Quarkus plugin there that just builds the optimized jar in this default setup. And there's a special profile for native, because native takes longer, and it probably wants to code with the optimized jar because it compiles faster, and when you are ready, you want to try the native. Good. So it has produced a simple REST endpoint, hello, like this. Okay. It has also produced a simple test, like this. There's a special Quarkus test runner that starts the application before running the test for you, and you can then use things like rest assured against the running application. It works with JUnit 4 and 5. Good. There's also a test for native. Of course, to run the test with the optimized jar, you can either run it from your IDE, because IDE or Eclipse and IntelliJ understand these JUnit runners, or you can run it using Maven or Gradle. This is an integration test that runs against the native executable, and there's a different runner for it. And the runner starts the native executable before running the test. You would have to use a different Maven goal for this, because it's an integration test. You would have to do Maven clean verify, and that would run first the unit tests, and then somewhere it should run the integration tests to this is surefire, and where's the failsafe? I don't know. Somehow didn't work. So good. Now let me show you the dev mode. Why is dev mode important and interesting? Because it reloads the code on the fly. So let's start it. Let's start it here. So it's running, and the process didn't finish. It's still Maven, but it's running. It's open, and we can change the message. The original message is here, and it's still hello. Let's change it to hello boo Bucharest, and it has changed, right? Yeah. What's interesting, when I change it, it's not reloaded when I save. It's reloaded when I hit the endpoint. Good. That's the dev mode. Testing native extensions. There's quite a lot of them, and to see the list, you can use the Maven plugin again. Here's the list, and you can also use the plugin to add an extension. So let's add the panache extension. And all it does is just to change the POM. It's not going to add any classes. Why have I chose the panache? Is because I find panache very interesting. Panache is a simplified ORM with Hibernate. Typically, with a Hibernate entity, you need to add a lot of annotations here for very simple things, and Panache eliminates all of that. All you need to do is to add the entity annotation and this superclass. You make all fields public, and it generates all the accessors, getters, and setters for you. Why is this good? Because it not only generates the entities for you, and you don't need to add so many annotations. You also have lots of code generated for you, and you can start using it immediately. You can call persist on the entity directly. You can check if the entity is persistent, and you can delete it. Then you can run queries using the entity class and using some static methods that are there for you without you needing to do anything. So, for example, you can find entities by ID. You can list entities by some filtering criteria. You can count entities, either all of them or by filtering criteria. And the same holds for deleting. There's more in Panache, like paging, sorting, a bit more simplified query language, and author-generated data access objects and repositories. That's basically it. In the last, for the last part of this presentation, the demo, there's just a few things I want you to remember from this presentation. It's all the good old Java. It's all the good old standards and libraries you probably know and use today. And it's a new level of efficiency comparable with Go, which is awesome. And this all makes Java a choice number one for cloud and serverless. So finally, some links where you probably want to go to try it up. Please do. Stack Overflow is the preferred platform for support. Ask your questions there and take them with Quarkus. People from the project are watching them and will hopefully answer your questions rapidly. Questions? That one? Microphone?
For the GraalVM, you said that we can't use threads even?
No, you can't. Or you can, but your thread pool needs to be aware of the limitations of the environment, and you can't use threads in static initialization. That's the main point. So you can use threads at runtime. There are thread pools that work inside Graal, because Quarkus is actually thread pool based at runtime, because there's Undertow under the hood for the imperative programming model. But it's not trivial. You need to know the quirks.
Okay, thank you.
The next question was here.
So I would like to ask you, if you are not using Kubernetes, what solutions do you have currently for service discovery and routing between the Docker containers?
Once again, in case I use Kubernetes, what?
So the question is, if you are not using Kubernetes,
not using.
What are the current solutions to deal with service discovery and routing between the Docker containers?
I don't think there's an opinionated answer to that at the moment.
Yeah.
So you probably have to look if your favorite service discovery would work out of the box, which it perhaps would do, because service discovery is nothing fancy. And it either works out of the box or you need to write an extension. That's it.
Thanks.
Any other questions over there?
Just a short one. Considering all those strives that have been made lately with the newer Java versions to optimize and minimize and stuff like that, so basically to improve performance and lower memory footprint and file size and stuff like that, would you say that this project will be able to keep up and I don't know, make my executable smaller and faster and stuff like that? Or would you say that eventually the standard Java, like the OpenJDK or whatever, will become more optimized than Quarkus? I mean, it's a question about the future of the project. Do you really think that this will,
The answer is I don't know. How to say?
You showed us the response time only for the first request.
That was not the response time. It was the time when the application is starting to serve your first request. It's starting to serve. That's not response.
Ah, okay. So, okay, I was wondering what's the response time for the next request, you know, but it doesn't apply.
That's easy to measure. Yeah, that's a good question. The question is if the native or I hope so. The question is if the native executable is serving requests faster compared to optimized jar and traditional cloud native stack. So the answer is no. It's typically not faster because the code optimization done by C2 on a traditional JVM is even better, but with the same amount of RAM, you can spin up more containers or more instances of the native executable. So you can run like 6 instances more with the same RAM, and through that you get more power. But if you are measuring response times for a single instance, typically the traditional JVM is going to be faster because of C2. But this might change in the future. But the difference is not big. That needs to be said. It's like, I don't know, 5-7%.
On one of your slides, there was Vault for CDI, as far as I remember.
There was what?
Vault.
Vault, yeah.
Vault, sorry. Is it still needed, actually, as everything is already done at build time statically?
It's needed at build time.
It's needed at build, okay. So okay.
Yeah, it's a special. It's actually a new implementation of CDI. It's not the old Weld. It's Weld Arc. A new implementation, and it needs to be said that it's not 100% CDI 2.0. Some things don't work because they cannot work in the GraalVM environment, and some things don't work yet because they were not implemented yet.
That's what I actually wanted to point out, right? Is it not very dangerous that we say that we have still CDI if we don't really have it, right? Because CDI, it's dynamic by its nature, right? And we don't have this dynamicness here anymore. Why do we still call it CDI? Why don't we just call it, I don't know, build time injection or something like this?
You can call it build time injection.
This
this is just an addition regards to the invoke dynamic you mentioned before. So invoke dynamic you mentioned it's just for lambdas, but it's also in case of indify string concatenation, and also for the constant dynamic now in JDK 11. So there are other options for invoke dynamic in JDK. But just an addition to what you have said.
Thanks. Question here? You wanted to ask another question?
Yeah, okay. So as I saw it from your presentation, this is really useful for serverless architectures. So you have really simple functions when you go to GraalVM because you have a lot of limitations. My question is, do you collaborate with, do you know what AWS does to optimize their functions to run fast and stuff like that? Or
I don't know that personally, and I guess somebody at Red Hat knows. I don't know.
Yeah.
No, you're asking is AWS are using GraalVM, or
and that also, yeah, I don't know.
I doubt it. GraalVM is too new to be used on AWS. I don't think so.
Yeah. Okay. Thanks.
Which native platforms are supported? The ones supported by GraalVM, which are at the moment, as far as I know, Linux, Mac, and Windows is being worked on, and either is there in some form already or will be there soon. Other questions? No questions? Thank you very much.